welcome to my class. In the previous video, I explained about what is the general method of divide and conquer approach. In this video, I will explain one of the examples under divide and conquer approach, that is binary search. But in this case, we are not going to conquer anything, and generally the conquering is required whenever we want to sort the elements. But here we are applying division procedure. We are applying division procedure for searching the element, but we are not going to conquer anything. Okay, just right away we are accepting all the elements and we are searching the given element. Now, I'll tell you one by one. So what do you mean by search? So what is searching? So generally, whenever any element is given as a question, and we need to verify whether that particular element or word is there in the group of words or group of elements. Generally, we prefer either linear search or binary search. Okay, na? But in linear search, we are going to linearly we sequentially search the elements from first element to last element, but there is no need of sorting the elements. But this binary search is requiring the element should be in sorted order. Elements should be in sorted order. So either elements are there in this set or array, or the words are there in the array, whatever it may be there in the array or given file. First of all, we must sort the elements. We must sort the elements by using any sorting technique, or while taking input itself, we need to take the input in sorted order. Okay, so that is the primary condition for binary search. Okay, suppose if you want to search any element x, so x is the searching element from the given array. Suppose one array is there, array with 10 elements or array with 20 elements. So generally, the array elements can be represented as a of 0 or a of 1, a of 2, so on, a of 0. If you start with 0, then a of 9. Or either in this way we can represent or access the elements, or we can also use this representation, lower subscript a0, a1, a2, so on, a9. Whatever it may be the representation, but either this one or this one is used for representing a0 or first element, and this one is used for representing last element. Either representation we can use for accessing the element or representing the element. So under binary search, first of all, we need to sort the elements in sorted order, any sorted order, either increasing or decreasing order, or we must enter the elements or words in sorted order list. Okay, then what is divide and conquer approach? What is divide and conquer approach? So generally, the divide and conquer general method initially checks whether the problem is smaller or not. Okay, na? So after checking whether the problem is smaller or not, we need to make the decision. Okay, if problem is very smaller, acceptable length is there, smallest length, then directly we get the solution. We will verify whether those two conditions are applicable for this one or not. Okay, na? If problem is very smaller or not, we need to check first. After that, suppose if problem is not smaller, then we need to verify whether if problem is larger, how this particular divide and conquer approach is used for binary search. I will show you. Okay, so initially, small or not, we need to check. This is the first condition in divide and conquer approach. Small means if problem is element problem, elements means array. Okay, na? If array is containing elements, if we take an array, this array is containing collection of elements. Or numbers. In this case, we want to search one element x. Here the array is given A, array is there A, and the searching element is X. Array is A and searching element is X. So what is the first case in divide and conquer approach? Smaller or not. How can you say whether problem is smaller or not? Suppose if the number of elements are 1. If number of elements are 1, there is no possibility of dividing problem into 2 or more than 2 problems. If number of elements are 1, the given element is X. Suppose that element, because we are if problem is very larger, we are going to apply this particular binary search recursively on subproblems, selected subproblems. Okay, suppose if that particular array is containing AI is the element, we selected one subproblem, that subproblem is containing only one element, we go on searching the elements like that or subproblems like that. At this moment we have one subproblem with one element AI. Okay, na? Ith element, and you are searching element is X. Okay, now then here problem is very smaller because that element that problem has only one element. then we need to search whether x equal to ai or not. If x equal to ai, the ultimate aim of any search procedure is seeing that yes, element is there in the list and also produce location number of that particular element, location number of that element. So if the number of elements are n, number of elements are 1, means the problem is very smaller. Problem is small, is acceptably small. If element related problem, if one element is there, that is treated as smallest subproblem or smallest problem. Searching element is x. Immediately under small constraint or condition, immediately verify whatever the element that is there in the array or selected subarray. If both are equal, searching element and the element which is there in the problem are both are equal, then we get that this particular procedure returns the location number I, because ith element is there in the problem, only ith element is there in the problem. Immediately we get result as yes, and the binary search returns the result is I. Along with this, it must return location number as I. Is it clear now? Suppose. So this is first case. If first case is failed, according to divide and conquer approach, after checking small as constraint, if small is failed, then the problem is larger. So that means there is no direct solution for that. Okay, there is no direct solution for that. But according to small, according to divide and conquer approach, there we mentioned S of P, because S of P was the direct solution. Solution for the problem, the S of P is the direct solution. Then S of P returns I if x equal to a of I, otherwise 0. Otherwise result is 0. So this particular procedure returns I value on S of P, or which returns 0 as a result if problem is very smaller. Problem is very smaller, suppose. So this is first constraint under divide and conquer approach. Second constraint is if it is else, means if number of elements are greater than 1. Number of elements are greater than 1. In that case, we simply treat that particular problem as relatively larger. Relatively larger. So assume that that problem is containing elements in the range I to j. In the range I to j. So I is the initial location number of initial element location number in the array, and j is the last location number in j. Then how can we represent elements? ai plus 1, so on, aj minus 1, comma aj. So aj is the last element, because first location number is I in the problem and last location number is j in the problem. Then the elements located or stored in that particular array are ai plus 1, so on, aj minus 1, aj minus 1, aj. Okay now. So once the problem is containing these number of elements and the location numbers are I to j, then you have to apply binary search. We have to apply binary search on this. One element is there, simply we get the solution directly. So we can represent binary search like this. Okay na? Where procedure representation is there, binary search. Suppose if you give binary search name as binary search, SRCH or search completely. Okay na? First mention array name, and mention initial location number, and mention last location number and search element. So binary search procedure is receiving four parameters now. First parameter is A, second parameter means array name, second parameter is initial location number, third parameter is last location number in the array, and fourth parameter is X. But what is the case in this? In small case, I equal to J. In this case, I equal to J, because only one element is there. That element itself there in initial location number, that element itself there in final location number, because that array is containing only one element. But here we are checking second case. Second case is problem is not smaller. And elements are there between I and j. Elements are there between I and j. I is initial location number, j is final location number. Then the elements are ai is one element, ai plus 1 is one element, so on, aj minus 1, aj. Aj is the last element, ai is first element. Or we can write it in this format also. A of I plus 1, so on, a of j. Either we represent the lower subscript format, or we can represent this square brackets format, we can represent array elements. But the binary search procedure represented like this with four parameters. First parameter is array name, second parameter is initial location number, third parameter is last location number, and fourth parameter is the searching element. Okay, now we are going to search element x. Here we need to take one location number. I will tell you what is the criteria for selecting location number, and assume that all the elements are in sorted order. Assume all the elements are there in sorted order. Okay, suppose if you select any location number q, any location number that is there between I and j. We are selecting one location number here that is there between I and j. I will tell you how we can select location number now. Okay na? there is a criteria for selecting location number, but once you select one location number q, okay na, in between I and j, there the element located in q is aq. There the element located in q is aq. Okay na? Here we get three possibilities now. Like that we can apply divide and conquer approach, and we can divide the problem into two problems. I will show you what are those two problems, and what is the middle problem, and what is the problem, what are the left side and right side problems. I will show you with three different steps. So the problem structure is this: if initial location number is I and the last location number is j, then we can write the problem procedure call like this. Okay, na? We need to call binary search on this particular problem with the low location number and high location number and array and searching element. I have already told, if you select the element q, location number q, for searching the element first initially, if you start at q initially, then we get three possibilities now. One is our searching element is x. If x equal to aq, because we selected q, I will tell you what is the criteria of selecting q according to divide and conquer approach. Under binary search, I will tell you what is q. Okay, na? Suppose if you select q, selection criteria I will tell you. If you select q, then the element is there at q is aq. Element present in q is aq. This q must be there in between I and j. Suppose if I is 10, j is 20, you must take q value either 10, 11, 12, 13 or up to 20. Selection criteria I will tell you after explaining these three steps. Okay. So after selecting q, then the element present in qth location is aq. Immediately compare this x, because our target is finding x value. If x equal to q, aq, then search is successful. Then this binary search returns q as result. Otherwise, we get two more possibilities. Those two possibilities are, if x is less than aq. All elements are in sorted order. Please remember, all elements are in sorted order. I plus 1 dot so on aj. Okay, na? So ai plus 1 so on aq dot aj. Here we selected this element. But all these elements are sorted. Okay. Now suppose the relationship is like this. After selecting a location, that location number element is greater than searching element. All the elements are sorted. We cannot go further because all these elements are greater than aq, because all these are sorted order. But the element x is less than aq. All the elements are sorted. Then we say that element may be presented left side of aq. Then how can we frame the binary search procedure now? What is the binary search procedure called now? Okay, if x is less than aq, then x is less than aq means that particular x value lying left side of aq, because all the elements are in sorted order. Then the binary search procedure becomes anyway array is a. Low location number we are not disturbing, because this subarray only we are going to select. What is high location number? Q minus 1, because we have already searched compared x with aq, that x is less than aq now. Then there is a possibility of getting that particular element from this array. Then what is the low location number? We are not disturbing low location number. Low location number is I only. But high location number is q minus 1, because one element left, one element less. So up to this portion we need to consider. Anyway, searching element is x only. We need to repeatedly apply this particular procedure. Okay, now otherwise, what is the third possibility? X is equal to aq is over, x less than aq is also over. Suppose x greater than aq. X greater than aq means, suppose searching element x may be presented or may not, but that value is greater than aq. We don't know whether x is there or not at the right side portion of aq, but based on that comparison, we got x value is greater than aq. Then we are expecting x value right side of aq now. Then what is the binary search procedure now? So binary search is array is a. I is disappearing now, because we need to start from q plus 1. Because from next element onwards we need to search x. So we need to select right side portion of aq. Then the location number right side q is going to be selected here. Then q plus 1 is the initial location number and j is the last location number, and element is x. Anyway, element is x. So like this we need to apply divide. See here, the problem is divided now. Once after selecting location number, after comparing that location number element with x, if x is equal to aq, then simply we return, because successful comparison has got, then aq is matched with x, then we got the successful result. Simply we are returning q. Second, suppose if it is failed, then two more conditions are there. One is less, another one is greater than. If x is less than aq, then we are expecting the x value in this portion. So from I to q minus 1 we must take. I to q minus 1 we must take. Suppose if these two are failed, only one more possibility is there, that is greater than. Greater than means we are expecting that x value right side portion of aq. Right side portion of aq. So in that case we are expecting x value here. Then what is the initial location number? The next immediate location number of q. Then q plus 1. Initial location number of this problem is q plus 1 and the last element location is j. So like this, we can divide problem into sub-problems. Like this, we can divide problem into sub-problems. That's why we say that this problem is coming under divide and conquer approach. Divide and conquer approach. Okay, na? So these are the possibilities. So based on these possibilities, we can search whether the given element is there in array or not. Like this, we can search the elements. Okay, na? Just by taking one example, I will explain this. After that, I will write the equivalent procedure. Once you understand the example, then we can easily write the procedure. After that, I will explain what is the time complexity of that. Okay. So I took 8 elements here in this array, and index numbers are 0, 1, 2, 3, 4, 5, 6, 7. Or you can also take index numbers are 1, 2, 3, 4, 5, 6, 7, 8 as you wish. You can start your array initial location number from 0, or you can take initial index number at 1. As you wish you can take. Okay, na? Suppose if you assume 0, 1, 2, 3, 4, 5, 6, 7 are index numbers. So like this, 8 elements are there. How many elements are there? 8 elements are there. Okay, na? In this array, 8 elements are there. Then I have already told in previous explanation, we have to select q. You have to select q in between initial index number and final index number, and based on that q we are going to verify 3 possibilities. One is aq is equal to searching element or not, or aq is less than searching element, or aq is greater than searching element. Suppose if you want to search element 4, x equal to 4, if you want to search element x equal to 4, then what is the criteria of selecting q? Simply we can calculate mid. Mid is the selection criteria. Just calculating mid is the selection criteria. That means mid location number is nothing but q. Mid location number is nothing but q. Then how can we calculate mid now? Mid is low location number plus high location number by 2. What is the low location number? 0. What is high location number? 7 by 2. Take floor. Floor means, suppose if you get resultant value is 3.5, then take 3. Our resultant value is 4.1 or even 4.9, you must take 4 only. Okay, na? I will tell you what is floor and what is seam. What do you mean by floor? What do you mean by floor? Suppose if you get 4.9, then we are taking 4 as the result. So 4 means the greatest integer value which is less than the given number, that is floor. This symbol is seam, but that is not required here. This symbol is seam. Suppose if you get 4.2, then you must take next immediate number. So how can we define seal? Seal is the smallest integer value which is greater than 4.2. The smallest integer value which is greater than 4.2 is called seal, and the largest integer value which is less than the given number is called floor. But here we are going to calculate floor now. So what is mid now? Mid is 0 plus 7 by 2. 7 by 2. 7 by 2. Then this value is 3.5. Then what is floor? 3 only. Floor is 3. Floor is 3. Okay, na? So the selection criteria for Q is blindly calculating mid. Every time we are going to calculate a mid, and based on that mid location number, we are dividing or we are applying 3 possibilities. Okay, na? I will show you by drawing one simple table. Take low as one column, high as one column, and mid as another column, because every time we are going to compare the given element at the mid location number. Okay, na? So what is low of this problem? 0 is low of this problem. What is high of this problem? 7 is high of this problem. What we got? What is the mid value? Mid location number is 3. Mid location number is 3. Then our aim is compare mid location number element with searching element. What is searching element? 4. We are going to search 4 and mid. So 4 is not equal to 8. 4 is not equal to 8. But what is the relationship existing here? 4 less than 8 is relationship. 4 less than 8 is relationship. So after comparing mid location element with the searching element, we got this relationship because searching element is 4, searching element x equal to 4, mid location number element is 8. So searching element is less than 8. I have already given 3 possibilities. If it is less than 8, then search the left side portion of mid. Search left side portion of mid. So left side portion of mid, low is low only, but I is 1 less than this location number. 1 less than this location number. Okay na? So what is low now? Low is 0 only. What is high? 2. Because mid minus 1. And mid is, what is mid? 0 plus 2 by 2. Mid is 1. Mid is 1. Mid is 1. Now, what is first location number? 4. What is searching element? 4. Yes, search is successful. Search is, in this particular example, search is successful. Then what is the location number now? Location number is 1. So immediately, this binary search procedure returns 1 as a result. Binary search procedure returns 1 as a result. So this is a successful search related example. If I take unsuccessful, I am also going to explain unsuccessful search. Suppose any number you take which is not which should not present in the given array. Initially I took the element present in the array and I have shown that within 2 steps I got the result. Within 2 steps I got the result. Initially I compared the element with third location element. Okay na? But the given element is less than third location element or mid location element. That's why I selected left side portion of the mid and the left side portion containing 3 elements. Okay na? Initial location number is 0, last location number is 2, then the mid location number is 1. Now I selected the first location number element and searching element. I made comparison between the first location element with the searching element. Both are matched now. Then 4 is equal to 4. Then I got search is successful. Then what is the location number now? Every time if search is successful, simply return mid location number. Simply return mid location number. So this is successful search related case. Suppose if I take any other element which is not present in the list. If I take any other element which is not present in the list. Okay. Now suppose if we take for unsuccessful search, what I am saying is for unsuccessful search. Suppose x equal to the number which is not present in the list, any number between 12 and 14 or 14 and 16 or above 16 you can take. Okay na? Suppose if you take 15. Suppose if you take 15. Okay na? So 15, x equal to 15. So what is the initial location number? 0. What is the final location number? 7. What is mid? I have already told 3. So what is third location number now? Third location number is 8. We are going to search 15. We are going to search 15. 15 not equal to 8 is correct. But what is the relationship exists between 15 and 8? 15 greater than 8. Earlier example, the x value is less than 8. That's why we selected left side portion. But here, searching element is greater than 8. Searching element is greater than 8. That's why we are going to select right side portion. We are going to select right side portion. Okay. So right side portion, how we get low location number? Anyway, we are not disturbing high location number now. So high location number is 7 only. We are not going to disturb high location number because we are searching, we are going to search this portion. What is low location number? Mid plus 1. Earlier example, high location number we need to update. High location number is mid minus 1 because the required element is maybe there in the left side portion. But here, whatever the number you took, that number is greater than mid element. So greater than mid element means we are supposed to select right side portion. We are supposed to select right side portion. Then this portion we are supposed to select. Then high is same. We are not going to disturb high because we are selecting this portion only. Then what is low? How can we get low? If you select left side portion, high is going to be updated, low is as is. If you select right side portion, high is not going to update, low should update. Low will be the next immediate location of mid. Next immediate location of mid. So mid is 3, next immediate location is 4. So that becomes low. So 4 plus 7 by 2. 4 plus 7 by 2 is 11 by 2. 11 by 2 means 5.5. But we are not going to take 5.5 now. We are going to take floor value. Floor value is 5. Floor value is 5. Then, now we selected this portion. That portion is 10, 12, 14, 16. Index numbers are 4, 5, 6, 7. Okay na? We got result is 5. Result is 5. So what is the fifth location element? 12. 15 not equal to 12. Yes, 15 not equal to 12. But 15 is greater than 12. 15 is greater than 12. Then you are supposed to select this portion. You are supposed to select this portion. Okay, that portion elements are 14, 16 are the portion element. What are the low location and high location numbers? Anyway, high location number is mid plus 1 only. 5 plus 1, 6, and 7 is 7 only. 5 plus 1 is 6. So low becomes mid plus 1. High is same as high only for the problem because we are selecting right side portion. If you select left side portion, we are not going to disturb low. Low is low only, but we are going to update high as mid minus 1. But if you select right side portion, high is same as high only for the previous problem, but low becomes low is going to change. The low we can get low as mid plus 1 because next immediate element, from next immediate element onwards we need to consider up to last element if you select right side portion or searching element is greater than mid element. Suppose if searching element is less than mid element, then we need to start with low and low to one element less than this, one location number less than this. Then mid minus 1 is the highest location number and low is as it is for left side element. Okay na? So low location number is 6, high location number is 7. Low location number is 6, high location number is 7. Okay na? Then what is 6 plus 7? 6 plus 7 is 13. So 13 by 2. 13 by 2 is 6.5. But we are not going to take 6.5, 6 only. So mid location number is 6. What is mid location number? 6, this one. Mid location number is this. Okay na? Then immediately compares 14 with 15. 15 not equal to 14. Yes. Yes. But what is the relationship here? 14 greater than 15 is the relationship. 14 greater than 15 is 14 less than 15. So mid location number is, the mid location value is less than 15. Mid location value is less than 15. Then searching element should be there at right side part. Searching element should be there at right side part. Then right side portion only one element is there. Now we got small problem. One element is there, location number is 7. Location number is 7. Okay na? So that 7 itself low location, that 7 itself high location number. Only one element is there, then I is a both are equal because if the problem starts with I and ends with the jth location number, but only one element is there means both are pointing same location. So here also after selecting 16, 16th location number is 7, that location number itself low, that location number itself high, then mid is also same. 7 plus 7 by 2 is 14. 7 plus 7 by 2 is 14. So which element is there in 16? 15 not equal to 16. Yes or no? 15 not equal to 16. But the relationship is 15 less than 16 is the relationship. But there is no left side path and there is no right side path. No subproblem is there at left side portion. No subproblem is there at right side portion. Then we say that element is not present. Then we get unsuccessful search. At x equal to 15, we get unsuccessful search. Unsuccessful. Then which returns 0 as a result. Then for 15, the binary search procedure returns 0 as a result. For 4, binary search procedure returns 1 as a result because 1 is the location number at which 4 is present. If you take 6, then binary search procedure returns 6 as a result, 2 as a result because the 6 is there at second location. Or like that, if you take any number which is present in the list, finally we get successful search. But the aim of binary search is producing or returning the respective location number as a result. So like this we can identify whether the element is there in list or not using binary search. I can also show you tree structure format because it is very easy finding elements using tree structure format for any number of elements, either n elements or n plus m elements or 10 elements or 5 elements. I will show you how we can generate or construct a tree structure format. So by using that tree structure, we can easily identify whether element is there or not. If element is there, in which location that particular element is there, I will show you this by constructing tree structure format because tree structure format is very easy for identifying the element. Okay, I will explain same procedure with tree structure format. Here, I am going to construct a tree with all mid location numbers. Okay, na? Suppose the same problem. If we take the same problem, previous problem, the problem is contained 2, 4, 6, 8, 10, 12, 14, 16, and 0, 1, 2, 3, 4, 5, 6, 7 are index numbers. Okay, na? So initially we are making comparison with mid of the whole problem. So initially, whole problem low is 0, high is 7 by 2. So what is mid? 0 plus 7 by 2 is 3.5. So that's why we take 3 as mid. So construct a tree with original problem mid. So original problem mid is 3, suppose. Now this is over. Okay, now suppose the given element is less than given element. How can we expand a tree structure now? Suppose if given element, this is first comparison. After that, either we compare the given element with x, given element with these elements if x is less than 8, or the given element x with these elements if x is greater than 8. Okay na? Suppose if x is less than 8, then we are supposed to select this portion. This portion. So what is the low index number? 0. What is the high index number? 2. What is the mid? 0 plus 2 by 2. So 2 by 2 means 1. So if you select left side portion, then immediately we are going to compare x with first location number, first index number location. So suppose if x is greater than a of mid, means if x is greater than third location number, then we are supposed to select this portion. Then low location number is 4, high location number is 7. 4 plus 7 by 2, 11 by 2, 5.5. Then 5 is the mid. Then next immediately, suppose if x is greater than mid, then we are going to compare element with 5, index number 5. Suppose if 1 is not matched, a low location number, suppose 4 is not matched with the given number, then either you select 0th index number problem or 2 index number problem. Yes or no? Because left side only one element is there with index number 0, right side only one element is there with index number 2. Suppose the given element is less than 4, means index number 1, the element is 4. If element is less than 4, then we are supposed to select this problem. If element is greater than 4, then we may select this problem. But here how many elements are there? Only one element. That index number itself low, that index number itself high. Then the mid is 0. Then finally in this portion we are going to search with 2. If 2 is not matched, then we say that search is unsuccessful. Otherwise, if the searching element is greater than 4 but less than 8, we may search second index number related element, because the only one element is there. That element index number is 2. Then low index number is 2, high index number is 2, mid is also 2. Their element is 6. Then we compare it with 6. If element is other than 6, then we say that search is unsuccessful, because we came to end. Otherwise, if you select the right side portion, then mid is 5, and the next immediate next step we are comparing with the fifth location element. If it is not matched other than 12, if you take, then but number is less than 12, then we go to this. Less than 12, only one element is there, that index number is 4. Then 4 plus 4 by 4, low is 4, high is 4, then mid is 4. Finally, we search the given element with 4. At index number 4, element 10 is there. Still, that element is less than 10 or greater than 10. We cannot find, because number is greater than 12. That's why we came to this direction. We came in this direction. But here, that number is 10. But the searching element is less than 10 but greater than 8. Search is unsuccessful. If number is greater than 10 but less than 12, search is unsuccessful. Otherwise, if the number is still greater than 12, then we select this portion. If number is greater than 12, we select this portion. In this portion, we have 2 plus 7 are index numbers. Then 6 plus 7 by 2 is 13. 13 is 6 in the index number. If number is less than 16, then there is no number is less than 14, there is no possibility of searching, because there is no subtree remained. Sub problem remained. But if number is greater than 14, still one more element is there at right side part. Take that element. Low is 7, high is 7. Then mid is also 7. If we compare 7th location element 16 with the searching element, if searching element is less than 16, there is no possibility of getting the element. Even searching element is greater than 16, there is no possibility of searching the element. Okay, na? But the beauty of this particular tree structure is we can say the answer immediately. Suppose if we take 2 as element, if you want to search 2 as element, x equal to 2, then immediately calculate mid is 3. Third location element is 8. Immediately compare 8 and 2. 2 is less than 8. In which portion we need to search? Left side portion. Then go to left side portion. So what is the mid location number of left side portion? 1. Element is 4. 4 and 2 if we compare, still 2 is less than 4. Then go to this portion. This portion mid location number is 0. But their element is 2. Then 2 and 2 both are equal. Then we got successful search, and simply procedure returns 0 as result. Then how many comparisons required? One comparison made at root node, another comparison made at this subtree root node, and third comparison made at this node. Okay now, this is successful search related. Even you select 16, start with mid of the original problem. Their element 8 is there. 16 is greater than 8. Then come this side. Then this portion mid is 5. This sub problem, right side problem mid is 5. Element is 12. Still 16 is greater than 12. Then go to right side. At right side we have two problems, but two elements. Mid is 6. Then compare 6th location element, that is 14, and searching element is 16. Then go to right side part. Right side part only one element is there. That element is 16. And 16 and 16 are matched. Then we say that search is successful. Suppose if we take 15, x equal to 15. Up to this is common. Up to this is common, and this one is also common because 15 is greater than 14. But after coming here, we are comparing 15 with 16. Search is not matched. That means elements are not matched. We are supposed to go left side part. There is no left side portion. Then we say that search is unsuccessful. For all unsuccessful searches, procedure should return 0. For all the successful searches, procedure should return bit location number. So like this, by drawing tree structure, we can say the answer quickly. Okay, now I am going to explain the procedure. Initially, what is the procedure syntax? Suppose if we take low location number is I and high location number is L and searching element is X and array is A. Initially, we need to verify whether the problem is smaller or not. This is small related problem, small. According to divide and conquer approach, first we need to verify whether problem is smaller or not. How can you say problem is smaller? If only one element is there, then we say that problem is smallest problem. How can you say only one element is there? If low location number and high location number both are same, like this. Here low location number, high location number both are same. If I equal to L, both location numbers are same, means only one element is there. If that element is I or L, whatever it may be, either you take AI or you take AL, because two location numbers are same. If X equal to searching element is exactly matching with AI, then return I is the result, else return 0 is the result. Because if for all unsuccessful searches, binary search procedure should return 0. For all successful searches, procedure should return mid location number or the selected location number. Okay, so only one element is there. I told you mid is I plus I by 2 or L plus L by 2. We get L only or I only. Here also we are returning mid location number or we are returning 0 if condition is else. Otherwise, suppose the problem is not small. This is containing more than one element. It means larger. Relatively larger. The problem is relatively larger. If more than one element is there, what we did earlier, just simply calculate mid I plus L by 2, then immediately compare mid location element with X. If X equal to A of mid, simply return mid is the result. Otherwise, what are the two more conditions? One is less than, another one is greater than. Greater than means else. If these two are not true, then obviously the default condition will take. Okay, na? Suppose if X is less than A of mid, means you are supposed to select left side portion. A left side portion means the low index number is same. Left side of mid is I is same, but highest location number is mid minus 1. Then the binary search procedure becomes like this. Else means equal to 0 is false, less than equal to A of mid is false, less than A of mid is also false. Then there is only one condition, that is greater than. Greater than means X should be there at right side portion, but we don't know whether the X is there or not. But we need to search right side portion of mid. Then we need to start from the immediate location of mid. Immediate location of mid is mid plus 1, and last location is L. So the binary search procedure becomes like this. Okay, na? So either this one, if X is less than A of mid, if X is greater than A of mid, then this one. Again procedure starts here. So if it is the case, then procedure starts with A, low location number is mid plus 1, high location number is L, and finally searching element X we take. Okay, na? So this is about the procedure. So whatever I wrote, I already explained in problem. So whatever the way we solved the problem, in that way only I included procedure statements. Then what is the best case time complex now? See, best case means if only one comparison is required to say the answer, then that is best case. Suppose original problem mid is matched with, suppose if you take 8. If you want to search 8, the mid is 8, searching element is also 8, then how many comparisons required? Only one comparison. Then best case time complex is 1. When one comparison is required, then the best case is 1. Then we represent best case as big omega of 1. Okay, now best case time complex is, if only one comparison is required, then we say that is the best case time complexity. Within one comparison, or just after calculating original problem mid, if that original problem mid location is matching with the searching element, then we say that is best case. Then what is worst case? Please remember, worst case means here if number is 7, after searching all the elements, if number is 7th location number, then 16, then this is worst case because finally we got the result. Or the worst case, if no element is present, the given element is not present, if the given element is not present, even that particular one is also treated as worst case. If element, the searching element is not present in the list, or the last element will be the searching element, last element in these three structures. Any path, if last element is the tree structure, then that is worst case number of comparisons for this problem. Okay, that worst case comparisons or average case comparisons we can calculate just by observing the tree structure. This tree structure is looking like a binary tree. Yes or no? Because this tree has left branch and right branch. Okay, in binary tree structure, if number of nodes are n, by using n number of nodes, if you construct a binary tree, then height of the binary tree is log n. Height of the binary tree is log n. Okay, so log n number of comparisons. Even in average case, we get the log n number of comparisons. Even in worst case, we get log n number of comparisons because the tree structure, if you construct any tree structure with n nodes, then obviously the log n will be the height. So in the worst case, we expect that particular element at the bottommost of the tree structure, or that particular element may not present in the tree structure. In that case, we are going to apply those number of comparisons. So that's why we need to reach the bottommost element in worst case and worst case. That's why the height, complete height, we need to reach in worst case. Then the log n, even average means log n by 2, that is not affected on log n. So average case and worst case, the log n will be the time complexity, and best case 1 will be the time complexity, because based on height only, based on tree structure height only, we say that these are the number of comparisons required in worst case. Okay, na? Based on tree structure only, if root node is directly matching with the searching element, only one comparison is required. Otherwise, based on number of traversals or based on number of steps we are traveling from root node to the bottommost, we say that these number of comparisons are required. See here, if you want to find 14, 3 comparisons are required. If you want to find 10, only 3 comparisons are required. If you want to find 6, 3 comparisons are required. If you want to find 12, one comparison is made at root node, another comparison will be made at this node. Then only 2 comparisons. So like that, once you construct tree structure, we can easily count how many number of comparisons required to say that this X is presented in the list, or X is not present in the list. Okay, so that's why best case is if root node is matching with the searching element, then only one comparison is required. That's the best case. And the worst case is based on tree height only. This tree looks like binary search. Binary tree. So that's why if you construct any binary tree with n nodes, then height is log n. Then the worst case is log n base 2 will be the worst case number of comparisons required. And average also, average means by 2 only. That same comparison. Anyway, we are omitting constant. Then 1 by 2 we are omitting. Then worst case and average case we get log n will be the time complexity, and best case the time complexity is 1. Here this is about binary search. In the next video I am going to explain the next application, that is merge sort. Thank you for watching my video.